So we're still in section 1.1 of our book that we're going to get today, and we'll talk about postulates today. So we're getting some foundations, like we said the other day. So we talked about our undefined terms. We came up with 8 definitions that we thought were really important the other day. We put them on our sheet. What we're going to do today is take those undefined terms and start doing some things, our undefined terms and our definitions, the things we defined, and start doing some things with them. So the first thing that we want to talk about is what we mean by intersect. When two figures intersect, that's going to be something that's important all year long in geometry. So what do we mean if in our everyday language? What does intersect mean? What are we talking about? Cross. Okay, that's one word. When they cross. Jordan? Like an intersection on the road, the two roads coming together. So coming together, or they meet. So, any other words that we think of when we think of intersection or intersect? Sorry. Cross, meet, come together. Those are good ones. So, in our technical definition, the way that we're going to use, the way we're going to talk about intersections in geometry, it has to do with this. But we say that two things intersect means, when two things intersect, it means they have points in common. Yeah, another way we could say it is that they share, when two things intersect, they share points. So that's what we mean when we say two geometric figures intersect. They share points. So when two things intersect, we have I've left out some letters there, intersection. So when two things intersect, we have an intersection, and Jordan says that thinking about two roads coming together at an intersection is one way we think about this. The intersection of two figures are the points that they have in common. So the points they have in common, or we can think of them as the points that they share. So if we think of the intersection in the road, the parts that the two roads share is all the parts in the middle of the intersection. So it's really the same idea. So an intersection is the points that the two things that come together have in common. And what we're going to talk about today are different kinds of intersections. You have a question? No. All right, so all the things that we're going to talk about today are what we call postulates. And we will talk about postulates all year long as well. Does anybody know what a postulate is? Anybody ever heard the word postulate before? No? All right, a postulate, we'll talk about postulates a lot. A postulate in geometry is something that we accept as true without proof. I'm sorry? Sort of like faith. In geometry, we'll talk about what we mean by postulate. It's something that just makes so much sense that it seems like it has to be, but we don't have any other way to prove it. We can't start with something else and get to our postulate. Our postulates are like our basic building blocks. We can't use anything to build up our postulate. We'll give some examples in just a second. So postulate's something we accept as true without proof. And we don't just make up any old thing for postulates. They make sense. But we just don't have any way to prove them starting from somewhere else. So all the things that we're talking about today we're going to list some postulates that have to do with our points, lines, and planes. So let's start listing our postulates. Our first one, and all of our postulates today have to do with intersections. The intersection of this is our first postulate. So this is one of our postulates. The intersection of two lines is, so let's think about what the intersection of two lines would be. If two lines come together, what do they share? What do they have in common? The middle point. So if I have two lines drawn here, so where they cross, what kind of thing is that? It's a point. Two lines intersect in a point. So the intersection of two lines is a point. So we're talking about our undefined terms, two of our undefined terms, and we're saying what happens when they come together. So the intersection of two lines is always a point. So that's our first postulate. Our second postulate, the intersection of two planes. Now this is A. So let's think about the intersection of two planes. If we have two big flat surfaces that come together, what do you think the intersection would be? We're thinking of just the places, just the part where they come together. So let's think about this corner of the room. Let's think of the plane here, this wall, and the plane here, this wall. What is the intersection? It's a line. It's that part, this sharp edge where they come together. That's the intersection. That's the part that they have in common. So like the corner of the room, the intersection of two planes is a line. So that's our second postulate about intersections. If two planes come together, they meet in a line. Our third postulate, and we talked a little bit about this one the other day, through any 2 points, is exactly one. What did we say? If we have 2 points, we can always make between 2 points. So here are my 2 points. What can we put through those 2 points always? A line. Through any 2 points is exactly one line. And we say exactly one because if I put my ruler here through the line, or through the points, and we think of the line going along the ruler, I can't connect those 2 points with a line in any other way because it wouldn't be straight, it wouldn't go between them. So any other way I try to connect those 2 points would have to be curved somehow, wouldn't be straight, or we couldn't make it work any other way than through that one line that goes through those points. So that's why we say exactly one. So that's our third postulate. Through any 2 points is exactly one line. And this next postulate we talked a little bit about the other day also. Through any 3 non-collinear so there's another one of our vocabulary words, collinear. Through any 3 non-collinear points is exactly one, what did we say the other day goes through any 3 points? A plane. And my example was the bottom of the legs of a stool. The bottom 3 legs of the stool are always going to sit flat. So through any 3 non-collinear points is exactly one plane. What happens if the 3 points are collinear? Did we talk about that the other day? If we think of this piece of paper, and I'm going to draw a line on my piece of paper. So the plane goes through this line. The plane of the paper goes through that line. I'm going to rotate the paper on that line. Now this new plane that's facing a different direction goes through that line, but it's a different plane. I can rotate it again, so I can rotate the plane around that line, so I get all of these different planes that are still going through that line. So if our points are collinear, our plane could rotate around that line and we get a bunch of different planes that go through the same line. So you could think of like a paddle wheel or something, all going through the line that's like the axle of the wheel. So that's why we have to say the points are non-collinear. We have one last postulate. If 2 points are in a plane, and I'm just emphasizing our undefined terms, if 2 points are in a plane, then the line through them, where do you think that line is? If the 2 points are in a plane and we have a line through the points, where is that line? So here's my line through these 2 points on the whiteboard. So I have 2 points on the plane of the whiteboard, and I have a line through those 2 points. Where is that line? Someone said it. Is it out here somewhere? It's on the plane. So if 2 points are in the plane, then the line through those 2 points is in the plane. There's no other way that we could put a line through those 2 points that wouldn't be on the plane of the whiteboard. It would have to be curved, it would have to bend around somehow to go through there, and then it wouldn't be a line.
What do you mean it would have to bend around? Where else would it be?
That's what we're saying. Where else could it be to go through those 2 points? It couldn't be anywhere else. And this is what we mean by postulates. Something like this just makes so much sense that it really couldn't be any other way. But we can't prove it starting from somewhere else. We can't start from somewhere else and say, okay, that shows that the line is in the plane. It just makes so much sense that we accept it as true. So that's why it's one of our postulates. So these are 5 of our starting postulates, the postulates that we're going to start with in geometry. And the really cool thing, I talked about Euclid the other day. Euclid started with a very small number of postulates. And he built all of geometry using logic on top of these postulates. So the postulates are our foundation, the postulates and our undefined terms, and we build this big structure of geometry all from these basic ideas. And that's really one of the, what Euclid did with geometry is one of the big achievements in mathematics, because we were able to use logic, and logic is a very powerful tool to build on these basic ideas and build this big system of math knowledge that we have. So that's one of the really cool things about what Euclid did with geometry and the power of the postulates and logic. So any questions on our postulates? All right, so before we end here, I have a couple of questions for you. How are geometric figures different from real-world objects? So if we think of some figure, we're thinking of a point, a line, a plane, something that we're making, an angle. How is that different from something in the real world? Okay. So a lot of the words and a lot of the ways that we use them, they're very similar. But I want to think. Let's kind of drill down a little deeper. How are they different? So what's the difference between a plane and my whiteboard? I can't rotate my whiteboard, okay? And I can do whatever I want with a plane. This is 3D. The whiteboard is 3D. Is a plane 3D? No. What did we say? How much thickness does a plane have? How thick was a plane? It was infinitely thin, right? It had no thickness. So does anything really have no thickness? Everything that we know about has some kind of thickness. What else? Anybody think of another way that they might be different? Real world objects and the things that we're talking about. Yes. Right. So we said that points and lines they exist in our mind. They don't really exist in the real world. So what we're talking about is kind of an ideal. They're these perfect things that exist in this world of math. We can apply some of the ideas to the real world, but they're not exactly the same. Next question: Why is 1 point not enough to name a plane? Why couldn't we name a plane with 1 point? Anybody have an idea? What are you thinking, Lyndon?
Nothing.
All right, so if we think of if the tip of my pen here is a plane, or is a point, here is the sheet of paper is a plane through that point. I'm saying the sheet of paper is going through that point. So if I name this plane with just that point, I'd be naming the plane with the tip of the whatever the point is at the tip of the pencil.
So it's not a plane without the point.
No, what I'm saying is, why can't we say that this is plane A, and have that be a good name for this plane? What if I do this? Is this a different plane? Does it still go through the tip of the pencil? Yes. So that's a different plane that goes through the same point. How about this one? Another different one that still goes through the same point. This one, another different one that goes through the same point. So that's why one point isn't good enough to name a plane, because a bunch of points could go, or a bunch of planes could go through that point. So if we said plane A, we could be talking about any of those planes that are going through that point. Next question, why are 2 points not enough to name a plane? We talked about this one a little earlier. Why can't we name a plane with 2 points? Two points, so we said that 2 points make a line. And what did we say a plane, if we tried to name the plane with that line, what could we do with the plane? We could rotate it around that line, so any plane that was rotated around that line would still be through the line. So it'd still be through those 2 points. So 2 points aren't enough to name a plane, because we could rotate around those points. Last question. Why is the order of the letters important when we name array? Why are the orders important? Because array only extends infinitely in one direction, so when we name it, we have to we have to tell ourselves what direction the array is pointing. The array only extends in one direction, so that's why the order is important when we name array. So any questions on our postulates? Yes, Chris.
Well, so back to I think it was first question, and where Jimmy said that this stuff feels like lines and intersections and stuff kind of they aren't like real or whatever.
Right.
Are existing, but you have the lines on there and it has like thickness, and it's existing up there.
So Preston's saying the lines I drew on the whiteboard are like real lines. If I took a ruler, couldn't I measure how thick that line was? It looks to me like it's about 4 centimeters thick. But a line. So we said a line had no thickness in any direction. So a line was completely, perfectly, infinitely thin. Impossible to measure. Right, you can't see it at all. We use these to represent it, but this isn't actually a line because it does have some thickness. This isn't actually a point because it's kind of, it's about as big around as my thumb. And we said a point had absolutely no size. So the point and the line are an ideal. They're perfect. They're completely thin. They're completely small. We draw them like this so that we can visualize them, but these aren't actually the actual things. Does that make sense?
Yeah.
Okay. All right. That's everything for the notes today.